All right, so there we go. So page 18. So this time will be, let me see if I can use the same colors for, all right, I use blue. So work done by a polytropic process, PV to the K equal to a constant. So this is a continuation. So case 2, if K equal either to 0 and 1, in that case, what do we have? PV equal to a constant, okay? Or over here, we could say that pressure will only be equal to constant over V. All right? So now we go back to the equation that the work done by the pressure is equal to the integral of P dV. So we substitute the P over here, so we get integral of C over V dV, or let's just write this as C dV over V, and let's say limits of integration would be V1, V2. All right, so this will give us what? So what is the integral of dV over V? This should be the log, no? Yeah, so it will give you what? C log of V between V1 and V2, which will give you C log of V2 minus log of V1. So, I mean, you could leave it this way, but if you remember the expression log of A over B is equal to what? Log of A minus log of B, no? Okay, so you could write this as work equal to C log of V2 over V1. And finally, what is C? So from this equation, C could be equal to what? C could be either be equal to P1 V1, or you could say equal to P2 V2, no? Yeah, because it's constant. So in this case, let's say it's equal to P1 V1. So at the end, you could just rewrite that equation as work equal to P1 V1 log V2 over V1. I mean, so basically, you see over here that you don't need to know this equation by memory. The only one I remember is this one. And then you can just substitute. No, I mean, the derivation here, I do it long, but really you could do it almost in 2 lines, okay? Here I do it in detail, but you could do that pretty quick. So you don't need to memorize these equations. All right, so let's do a summary. Help me a little bit. Let me go to the next page. doesn't look too good, but doesn't matter. I mean, I just did this, okay? Running out of pages, but I have another block. All right, so help me here a little bit. So summary of equations so far. So far, really the only two equations that you need to memorize are Q minus work equal to change in energy, and that the work done by the pressure is always equal to PdV. All right, this is the two you need to memorize. Now, work done by pressure we had three different cases. So the first one was when P constant. We said that the work was equal to P V2 minus V1. Okay, I'm going to go back to the previous page to add one little thing. The other case we did was for polytropic when PV to the K equal constant, when K different than 0 and 1. What was the expression we had? I think it's 1 over 1 minus K P2 V2 minus P1 V1. And the one we just derived when K is equal to 0, 1 for the polytropic process, we had that the work is equal to P1 V1 log V2 over V1. Okay, on the previous page here, I mean, it's not that important because we did the figure already for the previous case. But again, it's exactly the same figure. If you needed to plot this type of system, you don't know if it will be a concave or convex curve, so let me just do it this way, but the work is the area under the curve, okay? Just like over the other cases. All right, so now that I look at these equations, so let's say we are dealing with an ideal gas, okay? So for an ideal gas, what is the ideal gas relation? PV equal nRT. Is it N bar or R or the normal R? No idea. Okay, I'm going to check very quick. Doesn't matter how we define it, but we want to make sure we define it the same. All right, so let's see what is R over here, okay? All right, so let me just under this form. So if we write under this form, this equation can be rewritten as what? For an ideal gas relation, the above equation become what? So let's see, the first one, work equal to P V2 minus V1. Let's see, that one really has an advantage. So this one, since P is constant, that means that P1 equal P2, no? Yeah? So this one you have P1 equal P2, P is constant. So you could write this as just as what? N R T2 minus T1. Then the second one, which is work equal to 1 minus K, V2, V2 minus P1, V1. You could actually write this one as NR 1 minus K of what? T2 minus T1. And the third one, work equal to P1 V1 log V2 over V1 could be equal to what? NR T1 log. So let's see. If we use the ideal gas relation, what do we have here? PV equal nRT, which means that V I mean, we can keep V or we can write V. V will be equal to nRT over P, but adjusting is going to make it more complicated. So, I mean, so this could be equal to nRT what? P1 over P2, but I don't see if that gives any advantage, or this could be nRT1 log V2 over V1. I don't see any much of advantage on this one. But anyway, you see that you can combine these equations with the ideal gas relation. All right, now I'm going to do something to make sure that we use the same notation for this R. See, I'm not good at memorizing stuff. I like to understand stuff. To me, studying is understanding. It's not memorizing, okay? So you see in terms of R bar, I don't know too much. Okay, so here, let's do a line, and let's see what is really that R over here. So we have PV equal nRT, where N in this equation is the number of moles, which is mass divided by molar mass, no? And this is really the, I mean, this is not chemistry, but this is the number of moles. All right? So we can write that equation here. PV equal to mass over molar mass, RT, or I can rewrite it as P V over mass equal to R over molar mass T. Now, we defined in a previous lecture specific values. What was the definition of specific values? Is any constant that is in function of mass, no? So if you look at it, V over M is what? Is the specific volume, okay? And if we define here R bar as R over M, that way we'll be clear, all right? So we have this equation will become what? P, specific volume, R bar T. Okay. So the one of the bar is this one. Okay, so that means that R over here is the, can you see? The universal gas constant. that value should be on that page that I ask you to print with the units. That one should be on that page. So you should have it. You should have it in SI units, the same thing as US customer units or English units. Okay. So remember, you can bring that one to class. So the R bar, what is the R bar? The R bar is the universal gas constant for a specific gas. So how do you find the gas constant for a specific gas? You divide the universal gas constant by the molar mass of that gas. Okay? But right now, at least, all I did this stuff is to see really what is R and R bar. Okay? So R is the universal gas constant. R bar will be the specific gas constant for that gas. Okay? Where M will be the molar mass. Okay, but let's go back to these equations over here. Probably this one's on top. And let's try to do some examples, or a couple of examples. So page 20, let's say here, example. And the first example, I'm going to make it up. And then the second one, I took a program from the textbook just to have the answers. But it's going to be very identical. I'm just going to change the order. So for the below cycle, determine the work for each process. Okay, so this one will be symbolic, and the next one we do with values. That way I can make it up. It doesn't matter how you do it, they all look the same. What do you want to be? You want to go clockwise, counterclockwise? Let's do 1, 2, 3, okay? Doesn't matter. Okay, so this is just a direct application of what we just did. All right. So here we go. Process. One, two. What do you know about process 1, 2? It's a polytropic process. PV to the K equal to a constant. Let's say it's any K, okay? Will be what we just did. So you see that I'm not going to memorize the equations. I'm going to rederive, but this time faster. So you see that it's not really that long. Okay? So what is the general equation for work? PDV. Okay? So over here, if this is a polytropic process, P is equal to C over Vk. So this will be equal to what? Integral of C dV V over K. Now that's the one of the other day. So let's do like this a little bit different. This is actually the longest one. So this will be C integral of V minus K dV to do a bit. If I keep it the other form, generally you have a problem. What is the integral of x squared? You do x squared plus 1, so it's x cubed to the cube, no? X cubed divided by 3. So here what would be the integral of this will be C V of minus k plus 1 divided by minus k plus 1 over V1 and V2. This is the longest one actually. So I'm going to skip one or two steps. I mean, I'm not going to skip anything, but I'm not going to do very detailed either. So this should be equal to what? C over 1 minus k V2 to the minus k plus 1 minus V1 to the minus k plus 1. So now be careful, because that's where I'm going to do two steps in one. Because this is a polytropic process, what do we know about C? C can be equal to P1 V1 to the K or to P2 V2 to the K, no? So if I put this C close to this one, the C would be for this one, P2 V2 to the K. And if I put the C over here, it will be P1 V1 to the K. So if we do that, we find that the work 1, 2 for process 1, 2 is equal to 1 minus K P2 V2 minus P1 V1. And I give you about 30 seconds to think about it if you have to. Okay, what I've done. So the minus K will cancel out with the VK, no? Yeah? So we only have the V left. So I'll give you a few seconds to see what I've done here to here. Okay, so now we did 1, 2. Let's do 2, 3. This one is going to be very quick. Process. Two, 3. What is this process? This process is constant volume. So if you remember, I've been doing figures. What is the work? Is equal to the area under the curve, no? Okay? And by definition, what is the differential work done by the pressure? Is work done by the pressure equal to integral of P dV. In this case, since V2 equal V3, what's going to be the work? There is no area under the curve, no? So the work done during 2, 3 will be 0. All right? Because dV is 0. Basically, dV in this case is 0. There is no change in volume. But you could do it graphically, to check your answer. And now, the last one, process 3-1, what type of process would that be? That will be a constant pressure. So you want me to put it here. Here we have P1 equal P3. This will be here V1. And this one should be V2 equal V3. All right. So I'm done with this notepad. Let's move to another one. All right, so page 21. Now we do process. I have it over here. process 3-1. So this one we see that is constant pressure. Which means P3 equal to P1. All right? So it should be the area under the curve. So again, we take the equation, I don't memorize, equal to P dV. So this time we be careful here on the order, we integrate between V3 and V1, no? So this will give you, this is equal to P V1 minus V3, so we could say that work 3-1 is equal to P V1 minus V3. Okay. So, I mean, you see, this is pretty simple now. I just took one problem from the textbook with values, while you can look at the units to see if there's any problem with the units. So let's see what I have. So in the other example, is problem 225 from the ninth edition. You want to know. So let's say air contained within a piston cylinder assembly. Okay, so this is a good problem because, okay, air contained within a piston cylinder assembly. If you want to read the problem statement with you, you cannot read it. Can I zoom in with this? Yeah. Okay, so air contained within a piston cylinder assembly. So as soon as you see the term piston cylinder assembly, what I want you to do is a figure of a piston, okay? And it's not that important yet, but it will soon get important. And here you have air, meaning that what would be your system? This will be your system, okay? Let me zoom out. Okay, so remind me if I'm moving out of the page or something, let me know. All right, so what else do we know? Undergoes 3 processes in series. So let's say process 1, 2, compression, during which the pressure-volume relationship, so compression, for a polytropic process, but when K is equal to 1, and they give you that P1 is equal to 10 lbf in square, so PSI, V1 equal to 4 cubic feet, and P2 is equal to 50 lbf in square. Then about process 2-3, they tell you it's a constant volume, so it's good. So you say V2 equal to V3, and right away, what would be the work? 0, no? Yeah? V2 to V3, so a constant volume from state 2 to state 3, and you know that P and P3 equal to 10 LBF in square. So basically P3 equal P1. Okay, so obviously the last process 3.1, there is no other solution. Would be what? Expansion. And it would be a constant pressure. So you can write P3 equal to P1, and this will be 10. Okay, and they ask you to sketch the processes on a PV diagram and to find the work for each process. All right, so basically what we did before. Okay, so over here, I think the most difficult part is to do the figure. It's not really that difficult. So do the sketch. So P, V. And remember, I mean, I say that on the, I think on the second lecture, it's not that important, but remember we talk about intensive and extensive properties, no? What is V? V is one that you can add each one of them. It's like the mass, no? Mass of the whole class is M1, M2, M3. What about the pressure? It's a global, no? So you see it's one intensive, one extensive, no? All the time that you need to work with. Okay, so let's try to see how this will look like. So compression, compression means that the pressure is going to increase, no? All right, so what is the volume here? So V2 equal V3, and this is expansion, so that means that V1 should be higher than, V3, wait, let's see how this one will look like. So this is compression, the volume is going to go down. Okay, but at 2, the volume will be down. Okay, I think how this is going to look like, I know. So, I mean, my educated guess, let's say V1 will be here. Then we know V2 equal V3 will be here. And let's see what they say. First one is a compression. So we go from 1. And then if you compress, means that the volume becomes smaller and the pressure goes up, no? So what happened here, I'm pretty sure, is that we go from here to here on a polytropic process. You can sketch it convex or convex, it doesn't matter. This is the process that we know PV equal to constant. Now, what do we know about the other process? 2,3 is constant volume, okay? So that means that it's going to be along this line here. And what do we know? P3 is really equal to P1. So 3 should be here. So this is our second process. And this one, there is no choice to close the process, will be here. So what do we know here? V1 equal to 4. P3 equal to 10. Okay. P2 equal to 50. Okay, so to complete the figure, what do we need to do? We need to solve for V2, no? So how can we do that? Probably by just looking at process 1, 2. So, yeah, so let's say process 1, 2, what do we have? Is the polytropic process, PV okay, is PV equal to a constant, so let's say the work done, so PV equal to a constant, which means that P is equal to C over V. So the work done doing 1, 2 will be equal to P dV equal to integral of C dV over V. We know that C can equal to PV, so this will be equal to P1 V1, since we know P1 V1, log V2 over V1. Okay, but that's, oh, it's a lot simple, okay. Oh, it's a lot simpler than that. All right, so in order to find V2, sorry for that, okay, sorry it's not that organized, but to find V2, what can you do? From this equation, what can you say? So P1 V1 equal to P2 V2. So what can you have here? V2 will be equal to what? P1 over P2 times V1. So if I rewrite this equation, I try to leave it symbolic. What am I going to get? P1 V1 log. I mean, I could go and find the value, but so let's see. So if I substitute the V2 by P1 over P2, the V1 will cancel out, no? So we end up with P1 over P2. Yep. I mean, you don't have to do it that way. You can calculate this value and substitute. That's what I would have done if I had a little bit more space, no? Okay. So let's do a calculation with this and see what happened. So we need the figure. Oh, we need V2 anyway, so doesn't matter how we do it. To put it on the figure, what is V2? It would be P1, which is 10 over 5. So 4/5. So 0.125 times 4.4. Whatever value it is, okay? Is 1/5, which is, no, it's not 0.125. 0.8 cube, 0.8. So V2 is 0.8. Okay, so V2 over here, if you want, I just want to put it on the figure, would be 0.8. Okay, so you can substitute here 0.8 over 4, would be fine, okay? So we could do it that way. Anyway, I think we need to be careful here with the units, because P1 is given in what? Pound force per inch square. Volumes are given in what? Cubic feet, no? Okay, so we do the calculation, we need to be a bit careful. So page 22, when I write NA on my notes, that stands for, so I write it down this time, stands for numerical application. Okay, so let's see, we have to write down work 1, 2 equal to P1 V1 log of P1 over P2. All right, so So let's see what I need to do. And we need the work in BTUs. Okay, so here I don't have that page with the conversion, so but I might go and open it. All right. So we need to keep then the fit, I think, okay? So what is P1? P1 is 10 pound force per inch square, okay? So let's wait a second here. So they ask us to work in BTUs. So we know the BTUs is foot pound force. So that means we need to keep the fit, no, on the calculations. So let's go back over here. So we need to transform then the inch square into feet. I know you know how to do that, but how would you do that? Just know 1 foot is how many inches? 12 inches, no? So 1 foot square will be, you square everything. So it will be 144 inches square. And you see over here, this inch square will cancel with this one, and so on. And here we're gonna have log. So here we don't have to worry about the units because the top one, those units will cancel out. And from this point, we know that P1 is 10 and P2 is 50. I forgot the volume. You're absolutely right. And the volume is here. Volume was given to us to be, let's see, V1 is 4, no? 4. What did I do here? Oh, no, it's fine. Yeah, 4 cubic feet. Sorry for that. So, I don't know what will be the value, but what should be the units? So now we have this square over here, we'll cancel with 2 over here. So we'll have LBF per foot. So somebody gave me this result, it's 9,270.36, but they asked us to do that in BTUs. So what do we need to do next? We need to know that 1 BTU, I mean, I don't know it, but 1 BTU, we saw it on that page over here. 1 BTU is equal to what? 1 BTU is 778.17. So 778.17 foot LBF. So when I come here, I look at the unit transformation. All right. Okay, so if you do this calculation, you'll get that work 1,2 is equal to minus 11.91 BTUs. Okay, so you see that something tedious about this class are units, and this is nothing. They get a lot worse than that, okay? All right, so now the last process we need to look at is process we did 1, 2. Okay, so we did 1, 2. Now, process 2, 3 is going to be very quick. What should be the work between process 2 and 3? 0, because the volume is constant. So we can do for process 2, 3 is constant volume, which means dV equal to 0. So if you want, you can write down the equation, work 2, 3 equal to integral PdV, which means work 2, 3 will be equal to 0. Okay, and next will be process 3.1. You look at the figure, will be constant pressure. Okay? So you can say here for constant pressure, which means P3 equals to P1. We're gonna work 3.1 equal to P dV. But be careful because this is not between 1 and 3, it's between 3 and 1. So this is going to give us P of V1 minus V3. So again, we're going to have to be careful with the numerical application. So you see I just write n sub A here for numerical application. Well, some people say something else. Okay. Don't worry about those things, probably it's because, I'll go and check it at the end, okay? Okay, so I'll be this. Work 2.3, work 3.1 will be equal to what? P, so we can use either P1 or P3, and P1 or P3 is equal to 10. All right, you can see that from the figure. P1 equal to P3. So it's 10 LBF in square, so we have 10 LBF in square. That we need to do the same thing as before. Unit transformation, this would be 12 square inch square foot square. And now we need to do the V's. We can do the V at the end. So it will be V1 is equal to 4 cubic feet. And V3 is equal to V2. And you told me that that value was 0.8. Okay, we need to leave that in cubic feet. And since I have some space over here, I'm going to do the last transformation at once. That way you can give me the results. We need to have the results in BTUs. So this is 778.17 lbf per foot. So go ahead and do the calculation. Okay, so this gives you 5.92 BTUs. Okay, so we still have a few minutes, so let's do one more thing about this problem. All right, so let's look at the total work. It's not the solution, so you have to give me the numbers, but I don't really care about the number, but it will help. So the total work done by this cycle, would be what? Work 1-2 plus work 2-3 plus work 3-1. So, we just need to go. Work 1-2 was minus 11.91 plus 0, and work 3-1 was plus 5.92. Oh, so it's not going to be that complicated. So the total work would be what, 6.01? 5.99? Okay, I did it on the first. So 5.99, yeah, 5.99, but again, don't care that much about the value. What's interested here is that if we use the textbook notation, is that work done by the system. So this is, remember, this was our piston cylinder assembly, no? This is our piston. So if the work is negative on the textbook sign convention, what does that mean? Is on the textbook we had Q going in was positive and work going out to be positive. So if this is negative, that means that this is work done on the system, no? Yeah? So this is work done on the piston cylinder, work done on the piston cylinder.